Hello, I am Soil O from UIUC, and today I will talk about EcoCell, where we answer a fundamental question: can we save energy in cellular networks without any hardware changes? What's interesting here is that we focus on software side changes by reshaping the traffic before it reaches the base station. The motivation for our work is that cellular networks are a meaningful part of the global carbon footprint, and the main driver is the sheer scale of the infrastructure, even comparable to the aviation industry. There are around 6 million base stations worldwide, and one base station consumes around 30 tons of CO2 per year, so even small per site savings add up quickly. So, if we can save energy during normal operation, that's a big environmental and cost win. Most existing energy saving schemes fall into two buckets. First, using better hardware such as more efficient power amps or cooling. Or second, vendor side features like sleep modes or dynamic sector selection. But these changes are too slow to roll out and depend mostly on hardware changes of vendors. Therefore, we ask a fundamental question: can we reduce the energy consumption of cellular infrastructures without any hardware or vendor side changes? So our focus is the software side scheduling layer. Our main idea is if we can make smart decisions on scheduling how data is sent, can we reduce the base station's energy consumption only through software changes? To find where the energy wastes come from, we measure this by logging the power from a real base station, and at the same time, we sniff cellular telemetry using an open source tool called NGScope. The base station has a fixed, always-on cost it burns even when it's idle, such as cooling, which we don't count here. We measure only the dynamic energy, which is the extra power the base station spends because it's actively serving traffic. Our major findings are that base station energy scales with the extra work per delivered bit. In other words, there are many different ways of sending the same amount of data, and they can cost different energy if one forces more control overhead or more scattered transmissions. To give a short LTE refresher, in cellular networks, a subframe is a standardized unit used to transmit and manage data packets between the base station and the user equipment. Each subframe is 1 millisecond, and in each subframe there is a control part and a data part. The data part is divided into physical resource blocks. Think of them as little time frequency tiles. If you transmit data to a user through a subframe, you also must send control info telling them what they're getting and how to decode it. So subframes are not free. Each one comes with some overhead. We have three observations of the relationship between energy usage and traffic pattern. Observation 1 is intuitive. If you spread the data over more subframes, like on the left here, you pay control overhead more times. But if you pack the data into fewer subframes, like here on the right, you can leave other subframes empty, and overall, the base station does less control signaling. So the takeaway here is that more subframes mean more control overhead, which leads to more energy. So how do you pack data into fewer subframes? Our idea is to make traffic a bit more bursty. Instead of dribbling packets evenly across time, you can buffer briefly and then release a chunk at once. The same total amount of data, but it now arrives in clumps. That gives the scheduler a chance to fill the subframes more efficiently and leave others empty. We validate this idea with a microbenchmark. We implement this burstiness with a Linux 10 device to intercept traffic. All packets passing through this device is buffered for a certain amount of time, and here we try 4 configurations and measure the dynamic energy of the base station. We start with no buffering at all to transmitting for 0.03 seconds and then spending the rest of the 1 second idle. As transmissions get more bursty, the dynamic energy of the base station drops. It is because we can pack more data into fewer subframes, which reduces the number of control messages and cuts base station dynamic energy. So the important takeaway here is that burstiness can translate directly into energy savings. Observation 2 is about how many different users share a subframe. Like here on the right, if multiple UEs are served in the same subframe where different colors indicate different users, the base station needs more per user control signaling in that subframe. So if the scheduler can arrange things so that subframes like here on the right, where there are more single user at a time, it lowers overhead and also dynamic energy. Again, our observation is a simple rule. More UEs per subframe lead to more control overhead and therefore more energy. So how do you reduce sharing? We do this by reordering the packets before they hit the base station. Instead of feeding the base station a mix of subframes like here, we place them into separate per UE queues and then a round-robin scheduler that nudges the base station into giving a subframe mostly to one user at a time, which reduces control duplication. It's basically batching by recipient so that each subframe has less number of UEs. We do a small micro-benchmark where we apply this idea. When packets arrive, we place them into separate per UE queues and then a round-robin scheduler that dequeues the packets for each queue one by one. We start by saturating the cellular link with 5 UEs, each receiving UDP traffic at 20 Mbps. We find that over 60% of the subframes are shared by multiple UEs here before we do anything. We enable our UE segregation module 120 seconds into this experiment, which reduces the fraction of shared subframes near zero. Correspondingly, the base station's dynamic power draw decreases from roughly 8 watts to 4 watts. The takeaway here is that when less users share the same subframe, base station energy decreases. Our third observation is about radio conditions. Cellular networks uses something called MCS, modulation and coding scheme, and higher MCS means that you can transmit more bits per radio symbol when the channel condition is good. So instead of sending data at a lower MCS like here on the left, if you send the same amount of data when network conditions are better, you finish faster and spend less energy per bit. The takeaway here is that higher data rates consume less energy per bit. So the idea we use here is instead of transmitting data as it comes, we wait for a better moment and defer traffic to higher MCS and better network conditions if the traffic is delay tolerant. If you can defer a chunk of traffic until the channel improves, the base station can use a higher MCS and transmit the same amount of data using fewer resources. In this slide, we show the baseline run of our micro-benchmark. Here, a user device attempts to download a 200 megabyte file from the server, with the server download speed at 20 Mbps. We plot the network statistics and power over time. The important intuition here is regardless of the MCS and RSRP, the baseline keeps the throughput at a steady rate. So even when conditions are mediocre, you spend more time and resources for the same amount of data. It has a steady consumption of power, and it spends a total of 362 joules of dynamic energy for this file download experiment. Now with EcoCell style shifting, we try to transmit more when the channel supports a higher MCS, so you get more bits per scheduled chunk and less wasted work. You can see here that the throughput will follow the MCS and RSRP. So when the conditions are better, it transmits more, and when the channel conditions are bad, it transmits less. So as you can see here, it saves more energy than the baseline. So this is a concrete example of our observation. We send at a higher MCS when possible, which leads to spending around 12% less energy than the baseline. Now here is EcoCell in one picture. It sits before the base station and shapes traffic in 3 ways. First, temporal shifting. For traffic that can wait, we spend more data we send more data during better channel moments. Second, subframe packing. We add controlled burstiness so data fills fewer subframes. Third, we use UE segregation, and we group packets by user so fewer users share the same subframe. And the great part is that this can be a software middle box, so no UE or base station side modifications are needed. So what's the catch of EcoCell? The trade-off is basically energy versus quality. If you buffer to create bursts, you add a little bit of delay. If you defer for better channel conditions, you might add more delay, but only for delay-tolerant apps. So the rest of the results I will show now are asking, can we pick burstiness settings that save meaningful amount of energy while still feeling normal to the users? We evaluate EcoCell on real applications such as video conferencing and video streaming. We evaluate across 5 different bursting windows, which means we hold outgoing packets for this amount of seconds, then release them together as a short burst. So the base station can send the same data in fewer, fuller subframes at the cost of up to this amount of extra delay. We first show the headline result for video streaming. The QoE is measured by considering 3 factors: the video bitrate, the rebuffer rate, and oscillation. You can see here that the QoE is almost on par with the baseline even if we burst. This is because video streaming has a buffer which absorbs these short delays. We also measure the dynamic energy and see that compared to the baseline, at around 0.2 seconds of burst saves roughly 40% of energy with only 4.5% of QoE drop. For video conferencing, we also evaluate across 5 different burst windows. In this application, you can't push burstiness too far because people feel delay quickly. This bar plot shows QoE with metrics we care about, first the RTT, the normalized bitrate, and the frames per second. With a burst of 0.2 seconds, you can see that there is a slight increase in RTT and drop in bitrate. As you see here, we also measure the dynamic energy consumption for the different bursts. You can still save energy up to 30% with a burst rate of 0.2 seconds, but at the cost of RTT and bitrate. So EcoCell isn't just one setting for everything. It's more like a knob you tune based on the app's tolerance. To wrap up, EcoCell's key idea is saving base station energy by shaping traffic patterns, not by changing hardware or vendor software. It targets 3 energy waste sources: first, too many subframes; second, too many users sharing a subframe; and third, sending during bad channel conditions, and turns them into configurable behaviors like burst period and per UE batching. And the takeaway is practical. EcoCell is deployable today as a software sitting in front of a base station, and you can tune the energy QoE trade-off depending on the application. This is the end of my presentation. Thank you for your listening.